next we will look into an example of using register pair as loop counter for generating some delay. So, you see that in this example, so first this LXI B instruction, so it will load the register pair BC with the value 1000 hex. So, B register will get this 10 value and the C register will get the value 00. So, as a result total BC pair is now holding the value 1000 hex. Now, next instruction is DCX B. So, that will decrement the BC pair by 1 and this is actually this is decrementing the pair value by 1. So, actually the C value will become FF and this B value will be modified accordingly. So, next we need to check whether the BC pair has become 0 or not, and as we said that this DCX instruction does not affect the 0 flag, whereas the decrement the single register like DCR. So, that was decrement, that was affecting the status flags. So, this DCX instruction does not affect the flag register. So, we have to take a roundabout way. So, we move the content of C register to A register. So, move A comma C, and with the idea that when this BC register content will become 0, both the B and C register will have 0. So, we do OR A B. So, OR accumulator with the B register. So, A register has got the value of C. So, if both the registers B and C were 0, then this OR accumulator operation. So, this result will be 0 and the OR accumulator, the ORA instruction, this affects the status register or the status flags. So, the 0 flag will get affected. So, we can have a loop like JNZ loop. So, that will go back to this instruction whose label is loop. In different assemblers you will find slight variation, like sometimes these labels are written directly in this fashion, where there is just a space between the opcode and the instruction. In some cases you will find that there is a there will be a colon after this loop. So, that we have got this loop as a label. So, that is identified in some assemblers like that. So, next we will look into how to calculate the delay that is introduced. As I said that this looping is used mainly for this delay generation, because the code segment that we have seen, that is not doing any other meaningful job that way. So, for this purpose we need to know what is the time required for individual instructions. In 8085 architecture, so these individual clock cycles, so they are called the T states or time steps or individual clock steps, you can say. So, as you know that there is a crystal connected to the 8085 that generates a clock signal for it, and then the how many clock cycles are taken. So, that is documented in the manual for every instruction. What we will do is that we will essentially add all those clock cycles that are needed in different instructions, and knowing the frequency of the oscillator connected crystal connected to the chip. So, we can find out what is the actual delay produced by such a code fragment. So, the overall delay that is calculated is given by number of T states divided by the frequency. So, if we have got this MVI instruction, for example, if we look into the manual, you will find that this requires 7 such clock cycles or 7 T states. So, if the microprocessor is running at 2 megahertz, then this instruction will require about 3.5 microseconds to complete. So, that you can calculate, because that 7 clock cycles. So, that will turn out to be 3.5 microsecond for the microprocessor. So, in using this type of information, so we can calculate the time needed for any code segment. So, let us go back and to our first example of delay loop that we had, and try to see what is the amount of delay that it can generate. So, if this code fragment is put inside a bigger code, then it will introduce some delay in that code. So, we will and as I said that this is necessary many a times, particularly when you are doing some display part, say for which the display part which is meant for human being. So, our eyes will not be able to change locate the changes. Okay. So, I have to keep the display for some time. So, and if it changes very fast, then the eye will not be able to see that change. So, these delay loops are used for that purpose. So, we can use a loop to produce certain amount of time delay in a program. So, for example, if we look into this program MVIC FF hex, then decrement C and jump on not 0 loop. So, if you consult the manual, you will find that this MVI instruction takes 7 T states, then this decrement C. So, this instruction takes 4 T states and JNZ loop it takes 10 T states. Now, the first instruction, so that is the loop initialization instruction, like loop counter initialization. So, that is executed only once. If you look into this code fragment, that this particular MVI instruction is executed only once. The following instructions, that is DCRC and JNZ loop, so that is they will be repeated 255 times. This FF value is 255. So, it will be repeated 255. So, if you add these number two values of T states 10 and 4. So, total one iteration of this loop will take 14 T states. So, that is repeated 255 times. So, you can find out what is the time required. So, 255 into 4, that way it will come. Of course, there is another important issue, that the last iteration of the loop. So, JNZ will fail and require only 7 T states rather than 10 T states. So, this is a very, I should say, minute delay calculation, because this JNZ loop instruction. So, it takes 10 T state when the loop is successful, because in that case the program counter has to be loaded with the value from the memory, whatever is the instruction, this offset the loop. So, that has to be loaded into program counter. So, that takes time. Whereas, if it is not so, if the loop fails, that is if the 0 flag is set, in that case that last part of the instruction is not executed, where the program counter will be loaded with the value of this loop address. So, that is not executed. So, that requires some less clock cycles, and that is basically that requires 7 T states rather than 10. So, to calculate correctly, so we should deduct this 3 T states from the total delay from the loop, and the total delay of the program fragment is given by T delay is TO plus TL, where TO is the delay outside the loop, TL is the delay of the loop, and T delay is the total delay. So, if there are a number of instructions which are not in the loop, which are outside the loop, so they will contribute to this TO calculation. In our case, there is only a single instruction which is initializing the C register with the value. So, in our case, this TO is equal to 7 T states delay of the MVI instruction, and TL is 14 into 255 minus 3, because for the last iteration. So, it will the JNZ will not require that 3 cycles. So, it will require 7 cycles instead of 10, and that boils down to 3567 T states. So, 14 T states for the 2 instructions. So, that is repeated 255 times reduced by 3 T states, that is the for the final calculation of TL. Now, once this is calculated, so you can find out like what is the time needed, like this is the to T total that is required is 7 plus 3567, that is 3574 T state. Now, if you know the frequency of operation of the processor, so you can calculate what will be the total time corresponding to this value. So, this way we can calculate the time that is the time delays that are introduced by the delay loops. So, if we want more delay, then one way out is to use this register pair as a loop counter. So, let us look into the other program that we have taken as an example, where first this LXI B 1000 hex. So, the BC register pair is loaded with 1000 hex, then DCX B move A comma C ORA B and JNZ loop. So, if you consult the manual, then this LXI B instruction takes 10 T states DCX takes of 6 T states, move A comma C 4 T states, ORA 4 T states, and JNZ 10 T states. Of course, with the exception that for the last iteration JNZ will take 7 T states. So, once you know this, so in a similar fashion, so you can calculate the total number of clock cycles. So, T out TO, that is the delay that is introduced by the instructions which are not in the loop, that is due to the LXI in this example. So, that is 10 T states. Then inside the loop, so we have got so we have loaded with 1000 hex. So, 1000 hex corresponds to 4096 in decimal. So, this is and this sum of these T states is 6 plus 4 plus 4 plus 10, that is equal to 24. So, that 24 into 4096 minus 3. So, 3 is reduced because the last iteration will not take 10 cycles, it will take 3 cycles less. So, total is 98301 T states. So, 24 T states for the 4 instructions in the loop repeated 4096 times, reduced by 3 T states for the JNZ instruction in the last iteration. So, this way this calculation of TL will be done, and now you can calculate the total delay by adding TO and TL. Another way of incorporating delays, higher delay, is by means of nested loops. So, what we can do, like this is the overall structure of a nested loop. So, we initialize that loop 2, then this is the body of loop 2, then in the body of loop 2 initialize loop 1, and we have a body of loop 1, then we update the counter for the inner loop, and if this is the final count, if it is no, it goes back, the inner loop is repeated. If it is yes, then the counter for the outer loop is updated. So, this counter is updated, and then we check whether the outer loop has reached the final count or not. If not, it will go here and do the next iteration of the outer loop. So, in this way we can have these nested loops we can implement in assembly level programs by 2 registers for the 2 counters. So, for outer loop, loop 2 and loop 1, we can put 2 different registers to hold the count values. So, this is an example. So, here what we are doing is that MVI B, so 10 hex. So, B is loaded with 10 hex, that is 16. Okay. Then C is loaded with FF hex, that is 255, and then we do. So, this C this B register. So, this is used as the outer loop index, and C register is used as the inner loop index. Now, this decrement C. So, we are decrementing the value of C, and then we are checking whether the value has become 0 or not. If it is not 0, so we go back to loop 1. So, this decrement C and JNZ loop 1. So, they continue to be executed, and then once this C register becomes 0, then B is decremented, and then if B is not 0, then we go back to loop 2, where this C register is again initialized with FF hex, and the inner loop continues for some time. So, this way we can have nested loops implemented, and this can have more delay compared to say single register, or if the values are properly chosen. So, we can get better delay than the register pair as delay. So, for nested loops the calculation is similar, excepting that we have to the formula is applied recursively for each loop. So, we have to start with the inner loop, calculate the delay of the inner loop, and then we have to go to the outer loop delay calculation, where this inner loop delay will become a component. So, if we look into the previous program, then this inner loop, that is DCRC, then JNZ loop 1, etc. So, they will take a number of clock cycles. So, TO1, that is the outer loop 1, is the MVIC FF hex. So, that is this is it is that C register initialization instruction that takes 70 states. Then for the loop 1, the looping part, so that will take, as we have seen previously, 255 into 14 minus 3. Okay. So, that is 3567 T states. Now, so this is the total time needed for the inner loop. So, 7 plus 3567, so 3574, that is the total number of cycles t states that are needed for doing the inner loop for one iteration of the outer loop. Next, this outer loop calculation has to be done. So, in the outer loop we have got this MVI B 10 hex as the instruction outside the loop body. So, that will take 70 states, and this loop 1. So, what is the total time needed now? So, this is basically 16 times. So, the value was 10. So, that is so it will be repeated 16 times, 16 into. So, this 14 is the initialization part of this inner loop, okay, and plus this 3574 into 14 plus 3574. So, that will be multiplied by 16. So, these 14 T states are coming from the DCRB instruction and the JNZ instructions. So, this is basically from this. So, DCRB and this JNZ. So, they are actually taking that extra that 14 cycles. So, 10 plus 4 14. So, that is a part of the outer loop. So, they are included here. And this 3574. So, this is basically the T states for loop 1. So, that is repeated 16 times. So, this 14 plus 3574, this is the one iteration of the outer loop, and that is multiplied by 16. So, that we can get the delay for the outer loop minus 3, because for the last iteration that DCRB, the JNZ instruction will require less clock cycles. So, that gives a total of 57405 T states. So, total delay produced by that nested loop pair is 7 plus this 57405. So, 57412 T states. So, total delay introduced. So, if we assume that the clock period is 0.5 microsecond. So, that or this frequency is accordingly 1 upon 0.5 microsecond. So, it is total delay is 28.706 millisecond. So, this is the precise delay produced by this instruction the particular program with nested loop. So, this particular program, it has got the precise delay of 28.706 millisecond. So, this is the beauty of assembly language programming. So, if the same thing you do with high level language program, so we are not sure how much time these instructions high level instructions will take, because that depends on the way the compiler translates the program into machine code. Okay. But if you are looking into the assembly language, or you are writing the program in assembly language, then the programmer will know the exact instruction that is put into the program, and accordingly can calculate the delay, calculate the time needed for a program. So, that way these assembly language programs are very much important when you are looking for very precise timing information. How to increase the delay further? Okay. So, if you are not satisfied with whatever we have done, so you can introduce some dummy instructions like NOP, no operation. There is a special instruction called NOP that is there in almost all the processors, as well as in 8085. So, in the body of the loop you can put a NOP instruction. So, if you put a NOP instruction, so that will introduce some delay into the system, and that will be so one NOP instruction actually takes 4 clock cycles. So, in this program if I put a NOP here, okay, here or there. So, if I put a NOP, so that means the inner loop will be that the body of the inner loop will get extended by 4 more T states. So, instead of this being 255 into 14. So, it will be 14 plus 4 18. So, this value will become 18. As a result, this value will change, and that will finally affect the total clock. So, this value will get modified. So, total value this one will get changed, and that will affect the delay. So, you can put say a number of NOP instructions. So, if you want slightly more extended delay, so you can put a number of NOP instructions in the innermost loop, so that the delay value is increased. Next, we will look into another important issue, like the sequence of operations that are done in the microprocessor when some instructions are being executed. So, this is documented in the manual of any processor. So, if you remember in the architecture initial architecture lectures, we have seen like for doing operations like add R1 comma R2, we have to you have to activate some of the control signals in a proper sequence. Okay. So, here also the same thing, like now we know the 8085 architecture. Now, here also for doing some operation executing the instructions. So, we will need to we will need to control those a number of control signals, and 8085 the decoder and sequencer that exactly does this operation. So, we will look into some of the instructions and how they are executed over number of T states. So, that will be seen. So, this timing diagram, actually this is a representation of the various control signals generated during execution of an instruction. So, these are actually the signal lines that are monitored. Okay. The higher order address bus, lower order address bus, address data bus. So, this is as you know that this is multiplexed. Then the ALE signal, read, write and IOM bar. So, these are the signals that we will be monitoring for the timing diagram purpose. And as you remember that this read, write, so they are all complementary signal, read bar, write bar. So, they are active when the value is low, and this particular IOM bar. So, here also this is there is a bar. So, that signal means if the operation if it is doing a memory access, in that case this IOM bar line will be equal to 0, and if it is doing an input output from a device, then it will do this IOM bar line equal to 1. So, we will explain it as we proceed. To look into the first example, let us look into the instruction move a comma b. Suppose I have got so this move a comma b, it is stored at the memory location A000 hex. Okay. So, the first thing that has to be done is that this instruction has to be brought to the instruction register from the memory. So, if you look into the code of this, okay, so this move a comma b, the code is 78 hex. So, this operation of bringing this value 78 into the instruction register is known as the opcode fetch cycle or OFC. So, this will be called OFC or opcode fetch cycle. So, in this cycle the opcode 78 will be brought from the memory to the processor, the instruction register. So, this is the timing diagram. So, you see that the first so if I just go back slightly. So, you see in this address it is a 16 bit address, out of that this A0 is the higher order address byte and 00 is the lower order address byte. So, to put A000 on the address bus, A0 will be put onto the higher order address bus and this 00 will be put onto the lower order address bus. So, that is done. So, for the this entire operation opcode fetch cycle, it takes 4 T states. So, T1, T2, T3 and T4. So, T1 starts at this point, it ends at this point, then T2 starts at this point, it ends at this point, and these rising and falling edges of the signals they can be sampled by the memory to know the exact timing duration where the transitions are occurring. So, this higher order address bus, it is getting the value stable value from, you can say, after this T1 has come down, it has made a transition from high to low. So, this higher order address bus has got this value A0 in it. Then lower order address bus. So, when this is it is so at this junction. So, this the transition of this clock from high to low, by that time the lower order address bus will contain the correct value. So, this A0 is there in the higher order address bus and 00 is there in the lower order address bus, and the processor also generates the ALE signal. So, as you remember that there is a latch connected. So, this lower order address bus value 00 will be used by will be latched onto that external latch via this ALE signal, and this ALE signal is generated at the T1 clock state always. So, okay. So, at T1 cycle, so this is the ALE signal will be generated, and this ALE signal will be used to latch the value 00 onto the address latch, and then after that ALE becomes low, and so after this, from this point onwards, so that the address bus content is, the lower order address bus content is not meaningful, because ALE has gone low. So latch already has got the value 00 there. So for the memory, now A0 is in the higher order address bus, 00 is in the lower order address bus. So and the processor activates this read bar signal. So it is read bar. So far it was high, now it becomes low. So getting the read bar signal and the address A000, the memory will put the corresponding location content onto the data bus. Okay. So 78 hex it comes onto the data bus, and now you can say that this is actually towards the processor, from the memory to the processor, and you see that the write bar line. So this is continually high, okay, because this is not a memory write operation. So opcode fetch is a memory read operation, we are trying to read something from the memory. So this write bar line is continually high, and read bar line will become low for some time, between say from T2 to T3, this read bar line will be low. And this IOM bar line, so this line is low because this is a this is a memory operation, memory read operation. So this IOM bar line will be equal to 0. As a result, this is a memory operation. So so at the so you can see that by this time, by the junction of T2 and T3, memory is expected to put the value 78 hex onto the data bus, and the processor will be able to read it. And then in this part, so this T4, you see that nothing very significant happens in T4 as far as these signals are concerned. So what happens is that it is, though it is not documented, but it is expected that the processor is actually doing the decode operation at this phase to get the meaning of the instruction. So here it is doing the this is the opcode fetch cycle, and every instruction has got this opcode fetch in it. So the processor, so as I said that if you reset the processor, then it will be putting this program counter value onto the address bus. So it will, on the higher order address bus, the PC high will go, lower order address bus the PCL, the lower order 8 bits will go, and this ALE signal will be generated. Then this read bar signal will be generated, so that whatever is there in the content in that particular memory location, it will be copied and into the instruction register, and processor will try to execute that instruction. So again, after whatever be the meaning of that instruction, as soon as that instruction is over, so it will again generate the ALE signal, putting the PC high and PC low values onto the bus. So this way this opcode fetch operation goes on.